Hey, this video has the solutions for the 10-1 book problems, 5 through 29 odds. I was going to skip around, but it's pretty quick to blow through this whole assignment, and there's a lot of good stuff in here. As you will see, as you probably already are aware from discussion in class, it's a good review of limits also. So let's get into it. In number 5, we have the sequence where the general term is n over n plus 2 from n equals 1 to infinity. And they would like us to write out the first 5 terms of the sequence. It's kind of tedious, but not hard. And then determine whether the sequence converges, and if so, find its limit. So, first 5 terms. Plugging in 1, that's 1 over 3. Plugging in 2, we get 2 over 4. You could reduce that, but it's probably easier to see what's happening. These top ones just keep going up by 1, and so do the bottom ones. And so on. There's the first 5 terms. It's worth noting here, again, that to make things go up by 1 here, that means you have to have an n with a 1 in front. That's like kind of like the slope of what's happening here. They're going up by 1 each time, so you need a 1. And then a plus 2 just shifts things. To figure out if it converges or not, we have to find the limit as n approaches infinity of the general term. And if this limit exists, then the sequence converges, and it converges to this limit. This limit is a highest power, right? Remember that? Highest power is the same on the top and the bottom, coefficient 1 over 1, so that limit is 1. So it converges to 1. Excuse me. And what that means is, as you go further and further and further out in this list of numbers, they get closer and closer to 1. Right. Number 7. We have the sequence, kind of a boring sequence here. There's no place to put the n. The terms in this sequence are just 2. It's 2, 2, 2, 2, 2, etc. What's the limit as n approaches infinity of 2? Well, it's 2, right? There's no place to plug the n in. So this sequence converges to 2. In fact, it's always just equal to 2. Number 9. This is getting more interesting now. Natural log n over n. N equals 1 to infinity. So that's going to be equal to natural log of 1 over 1. That'd be 0, right? Natural log 2 over 2. Natural log 3 over 3. You get the idea. Natural log 5 over 5, etc. A little bit more interesting question is, what's the limit? Is the sequence converging or not? So how do we do that? Well, if I just plug in infinity, it's infinity over infinity, so that's not helpful. But it is an indeterminate form, so I can use L'Hopital's rule. So that's equal to the limit as n approaches infinity. Don't be lazy now. Please write this out. Derivative of the top, 1 over n, over the derivative of the bottom, and that's just 1 over n. And as n approaches infinity, 1 over infinity, that goes to 0. So it converges to 0. And I guess they asked that, so I should be, I think I'm being a little bit lazy here. This converges to 1. This converges to 2. And this one converges to 0. Number 11. We have the sequence 1 plus negative 1 to the n. Remember, this is our sign flipper. Every time n is odd, this will be equal to negative 1. Every time n is even, this will be equal to 1. So when I plug in, from n equals 1 to infinity. So when I plug in 1, that's odd, this will be negative 1. 1 plus negative 1 is 0. When I plug in 2, that's equal to positive 1, so 1 plus 1 is 2. And then I get 0 again, and then I get 2, and then I get 0, and so on. And there isn't really, we can't really deal with a sign flipper with limits in the same way, but we can just look at this and say it's kind of like doubly converging, like every other term converges to 0, and then the even terms converge to 2. But that's not convergence. Convergence has to be, the whole thing has to be getting closer and closer to some number. So this diverges. Or does not converge. Sometimes we say it's divergent. Number 13, we have a sign flipper, and we have 2n cubed over n cubed plus 1 from n equals 1 to infinity. So let's see, when I plug in 1, that's odd, so it's going to be negative, and then 2 over 2, and then next term will be positive because they're alternating. When I plug in 2, let's see, that's 2 cubed is 8, so 16 over 8 plus 1, which is 9. Next one's going to be negative, the signs will alternate. When I cube 3, that's 27, so 2 times 27 is 54, over 27 plus 1 is 28. No advantage really to reducing these. Then the next one's positive, and that's, I plug in 4, cubed is 64, times 2 is 128, over 64 plus 1. And finally, when I cube 5, I get 125, so that's 250, this one's negative. 250 over 125 plus 1 is 126. So there's the first 5 terms. And then I want to find the limit as, I'm going to ignore the sign flipper for a minute and just find the limit of the part of without the sign flipper, right? And by the highest power rule, that's 2 over 1, so that's 2. So, well, that looks kind of promising, but it's sign flipping, right? So that means half the terms are going to be going to 2 and half are going to be going to negative 2. So this goes to 2 and negative 2, so this diverges. And maybe it's worth noting here that if you have an alternating series, alternating sequence of numbers, the only way an alternating sequence can converge is if it converges to 0. Because if you're alternating, you'd have to be getting closer and closer to 0. That's the only number. 0 is the only number that's equal to the negative of itself. If it was converging to anything else, you'd have 2 different things that it was trying to converge to, and that's divergence. So that's good to note there. Number 15, we have the sequence n plus 1 times n plus 2 over 2n squared from 1 to infinity. First 5 terms. When I plug in 1, bottom's 2, and then on the top I have 2 times 3. Next term, when I plug in 2, the bottom 2 squared is 4, so on the bottom I have 8. And then at the top I have 2 plus 1, 3 times 4. Next I have on the bottom 3 squared is 9 times 2 is 18. And then 4 squared times 2. It's sometimes easier to just focus on 1 if you have to do this mundane exercise, right? Double all of the squares. So that's 1 doubled, 4 doubled, 9 doubled, 16 doubles, 25 doubled. And then on the top, I had, this was 2 times 3, 3 times 4, 4 times 5, 5 times 6, and 6 times 7. For the, well, I don't know, for the more mathematically curious of you out there, for what it's worth, these are the twice the triangular numbers here. And ask me about that if you're interested, but that's a thing. Okay. What's the limit of this sequence? Does the limit exist? Does it converge? And if you multiply this out, if you FOILed it out, then you're going to get an n squared in the front. So I have highest power top and bottom. It's 1n squared on the top and 2n squared on the bottom, so that's 1/2. And it's not alternating, so that converges. Converges to 1/2. Number 17, the cosine of 3 over n. Excuse me, so what's happening here? I have, first term would be cosine of 3, then cosine of 3 over 2, and then cosine of 3 over 3, and then the cosine of 3 over 4, and then the cosine of 3 over 5, etc. None of those are nice numbers, right? These are all angles measured in radians, so it's all garbagey looking numbers. And there's no reason to put them in your calculator and do that. So what's the limit as n approaches infinity of the cosine of 3 over n? So this is the kind of limit, we saw these in chapter 2, where you have to work from the inside out. This, as n goes to infinity, 3 over infinity goes to 0. This is going to 0. So what's the cosine of 0? It's 1. So this converges to 1. So it might be tempting to look at this and say, oh, this is 0, so it just converges to 0, but it's cosine of 0, right? So it converges to 1. Number 19, we have n squared times e to the negative n, which is the same as e to the n on the bottom. And I think I'm going to write them like that. So when I plug 1 in, I get 1 over e to the 1. When I plug 2 in, I get 2 squared, and then I'm going to get 3 squared, and then I'm going to get 4 squared, and then I'm going to get 5 squared. Let's do the tops first. And on the bottom, I'm going to get e to the whatever, right? E to the negative 2, same as e squared on the bottom, then e cubed, e to the 4th, e to the 5th. So what's the limit as n approaches infinity? And here it's definitely helpful to write it as n squared over e to the n. If you plug in infinity, you get infinity over infinity, so we can L'Hopital. So that would be 2n over e to the n. That's still infinity over infinity, so I'll L'Hopital again. And then I'll get 2. As soon as I get something, just a number, that means I'm going to get an answer here. It's not going to be L'Hopital anymore if I have a 2 on the top. Over e to the n, that's 2 over infinity. That goes to 0. You might have suspected that, right? These e to the whatevers are going to grow much faster than those. So this converges to 0. And number 21, this is the last one of this type of problem. So we have n plus 3 over n plus 1 all to the n power. N equals 1 to infinity. Excuse me, so when I plug in 1, I'm going to do the inside parts first. Plug in 1, I get 4 over 2, and then each of those are, since there's 1s, are the coefficients of the ends, that's like my slope. So then it's going to go 5 over 3, and then 6 over 4, and then 7 over 5, and then 8 over 6. And then the powers are just the n powers, so that'll start first power, second power, third power, fourth power, fifth power, like that. Dot, dot, dot. What's the limit of n plus 3 over n plus 1 to the n? If you plug in infinity, you get, this is highest power, top and bottom are equal, coefficients are 1s, so this goes to 1 and this goes to infinity. 1 to the infinity is an indeterminate form, and it's an indeterminate form that's suggesting to us that we can do the L'Hopital trick where we set this equal to L, and then we take the natural log of both sides to get this down. So let's do that. So let's limit as n approaches infinity of the natural log of n plus 3 over n plus 1 to the n, but the reason that we do this is so that I can bring the n out to the front. Right? It's going to be equal to natural log of L. And then this right here, it can be L'Hopital. It can be turned into a L'Hopital form if I move this to the bottom as n to the negative 1. So that bottom part is going to look now like natural log of n plus 3 over n plus 1 over n to the minus 1. So now after a couple steps, this is the like version 3, the third face of L'Hopital, where you have to first introduce a natural log and then you have to flip. So like 2 steps to get it into the L'Hopitalable form. And now I can do L'Hopital. We can just check to see that now this is actually going to be n. If this is going to 1, natural log of 1 is 0, and then 1 over infinity, that's going to 0 also. So now I can L'Hopital. That's the limit as n approaches infinity of, I don't know if I have enough room here. My goodness, this could get a little bit messy. Let's see. So the derivative of the top, derivative natural log of this is 1 over this, and 1 over that flips it over. So that's n plus 1 over n plus 3 times the derivative of what's inside. The derivative of what's inside this, using the quotient rule, is low d high, which is 1, minus high d low is also 1, over low, low. That's the derivative of the top. Right? The derivative of the bottom, derivative of n to the negative 1, is negative 1 n to the negative 2. Now, if you just plug in infinity again here, you're going to get 0 over 0 again. But what we need to do here is clean this up first and simplify it. So let's see if we can do that. One of these n plus 1s cancels. And here, this does not cancel. That would be bad algebra. This is n minus n, and then 1 minus 3. So on the top of the top, sorry, let me write this first. So I'm not being lazy. I'm not going to set a bad example for you. This is negative 2, right, over, on the bottom I have the n plus 3, and one of these n plus 1s, the one that didn't cancel. Then here, n to the negative 2 on the bottom is the same as having negative n squared on the top. So the negative signs cancel out. So on the top I have 2n squared, and on the bottom I have n plus 3, n plus 1. So hey, that's highest power. Top and bottom are both 2. Coefficient on the top is 2. Coefficient on the bottom is 1. So that's 2. But that's equal to the natural log of the limit we were looking for. So what's L? L is equal to e squared. So that might be a kind of surprising result, or maybe you remember that that's what happened with that kind of n to the n power thing that we often end up with e's in the answers. So that's cool, I think. So that means this converges. And it converges, maybe surprisingly, to e squared. Groovy. Now, moving on. Wasn't that a great review of limits? Come on. Number 23. Here, they're giving us the first few terms, and they want us, so going the other way, they want us to write the little curly bracket thing, the general term. 5, 6, 7. And this is good practice for how to figure out how to write these patterns. So that's equal to, on the top, I have 1, 3, 5, 7. So that has a slope of 2. It's going up by 2 every time. So it's 2n plus or minus something. On the bottom, it also has a slope of 2. I'm going to leave this part blank first. And then if I'm going to start at n equals 1, which they asked us to do, then the way you figure this number out, I think the easiest thing to do is just plug in the first number and see what it has to be. So if I plug in 1 in here, I get 2, which is in fact the correct number. So I don't need anything here. And you can try for n equals 2n, 2 times 2, 2 times 3, 2 times 4, that's right. And then on the top, if I plug in 1 here, I get 2, but I want it to be 1, so I need to subtract 1. And then you can check those. So that's numbers, patterns where it just increases by the same amount. You need your slope, how much it's going up by each time, and then you just adjust so that the first number is the right number. So there's the general term. Does it converge? Well, now we're back to doing what we just did before. What's the limit as n approaches infinity of 2n minus 1 over 2n? Highest power, top and bottom, are the same. So 2 over 2 is 1. So it converges to 1. Number 25. Now we have 1 over 3 minus 1 over 9 and 1 over 27 minus 1 over 81 and so on. On the top, we just have 1s and the signs are alternating, so I need a sign flipper like that. We'll see if n works or not. We can do that right now. So if I plug in n equals 1 here, then that would make the first term negative. But I don't want the first term to be negative. I want it to be positive. So to get it to shift over 1, I put a plus 1 there. And now when I plug in 1, I get an even number, and it will alternate from there. So that will make my first term positive. So this is always going to be either n or n plus 1, depending on what you need that first term to be. And then on the bottom of 3, 9, 27, 81, I think you just have to recognize here, it's not going up by the same amount every time. If you stare at that for a minute or two, or I don't know how long, you got to realize that this is 3 to the first, 3 squared, 3 cubed, 3 to the fourth. It's 3 to the n power. And we just have to recognize that. And what's the limit? So leaving my sign flipper out for a minute, what's the limit as n approaches infinity? 1 over 3 to the n. Well, that's 1 over infinity, so that's going to 0. And it's sign flipping, but that's okay if you're going to 0, right? Because negative 0 and 0 are the same thing, so it is going to converge to 0. Remember from before that you can converge with a sign flipper so long as it's going to 0. Any other number would not work. Number 27. We've got terms 1 minus 1/2, 1/3 minus 1/2, 1/3 minus 1/4, and so on. And it's a little tricky. This is, I think, a more challenging one to come up with a general term. The first thing that I think it'd be very helpful to recognize is that this is the same as negative 1/2 minus 1/3, and then positive 1/3 minus 1/4, etc. That makes it a lot easier to write this, because then we realize that there's a sign flipper. First term's positive, so I'm going to want that to be n plus 1. And then we have 1 over n, right? 1 over 1 minus 1 over n plus 1. So 1/2 minus 1/3, 1/3 minus 1/4, always 1 over n minus 1 over n plus 1. That's the general term. A little trickier there. Now we'll ignore the sign flipper for a minute and see what this does. So it's the limit as n approaches infinity of 1 over n minus 1 over n plus 1. If you just try to plug infinity in, you get 0 minus 0. And 0 minus 0, hey, guess what? That is not indeterminate. Infinity minus infinity, that's indeterminate. But 0 minus 0, if both of these things are going to 0, then the difference between them also should be going to 0. If we want to really drive it home, let's see what we can do here. We can get a common denominator. So it's the limit n approaches infinity of 1 over n, so common denominator n plus 1 here. That needs an n, and then the common denominator would be n times n plus 1. That's a little bit of algebra for you there. So the n's cancel out. So you get 1 over n times n plus 1. Highest power is on the bottom, n squared, so that drives it down to 0. So it is sign flipping, but it's going to 0, so that's okay. So it converges to 0. And last, we have the square root of 2 minus the square root of 3, and then the square root of 3 minus the square root of 4, and then the square root of 4 minus the square root of 5, etc. So what's that in general? That's the square root of, if I'm starting at n equals 1, then it's 1 bigger than 1, and then minus the square root of 1 bigger than that. Right? They're going up by 1, 2, 3, 4, so the coefficient in front of there is just 1, and then you just have to add or subtract whatever you need to get the first term to line up. So that's that. Now what's the limit as n approaches infinity of the square root of n plus 1 minus the square root of n plus 2? If you plug in infinity, that gives you infinity minus infinity. And we've seen recently that, we've been reminded recently rather, that is an indeterminate form. And indeterminate form means you got to do something. Now, I know it's been a while, but the thing we have to do here, back to the olden days of chapter 2, when you see square roots like this, plus or minus in between, we have to multiply by the conjugate. And to keep it intact, equal to the same thing, I multiply by the conjugate top and bottom. That gives me, when I do that, this is the difference of two squares. That gives me n plus 1 minus n plus 2 on the top, And on the bottom, I have the square root of n plus 1 plus square root of n plus 2. On the top here, n minus n cancels. 1 minus 2, that's negative 1. That's what that's equal to on the top. So I have negative 1 on the top, and on the bottom here I have infinity plus infinity. Infinity plus infinity is not indeterminate. Infinity plus infinity is infinity. So I have negative 1 over something that's blowing up, so that's going to 0. And this was not even alternating. It wouldn't matter because it's going to 0, but this converges to 0. And that, my friends, is what we need to do with sequences. And although you knew about sequences before, you didn't know about limits before. So this adds to what we can say about sequences. And that is that.